confused about why you wanted to have like 2 different projects for the assignment, and so I was asking other people under the same sort of thing.
What's my thinking?
Yeah,
or
do
just
we have to, or what?
Well, so they're 2 totally different deliverables.
Right.
So my thinking is, one is a data set that you're analyzing, potentially to write up, depending on how far you want to push it. So that should be emphasizing your sort of ability to, or help you foster your ability to use data and do some of the basic regression stuff in the context of a research project.
Yeah.
The other one is a proposal,
Right.
which is more conceptual at this point, but needs to be thinking about potential data sources, research questions, and analytic techniques specifically designed to go after a causal research question. So they're really 2 different parts. I mean, they're obviously related. Can be, I mean, the normal cycle might be write a research proposal, get funding, do the research. We don't have time to see that through, obviously. So I want to give an opportunity to start on a research project kind of in hand where there might be a deliverable if you want, like I said, if you want to push it that far, while you're thinking potentially bigger in the context of a proposal. So as I said before, they could be overlapping topics, but one is analysis of data in hand, one is looking forward to, you know, your research agenda and writing something that is of interest to you potentially down the line.
Okay.
So I mean, if you could, it doesn't make sense to write a proposal to do a project that you could already do, although in reality sometimes that actually happens. You write proposals for projects you've already done. But you don't tell people that. I already know what the answer is, but give me the money and I'll tell you. But since I'm the one who's assigning both, I can kind of, I'm not having money anyway, so the proposal's not, I mean, the proposal's for me for class because you've got to do something. Because I have to grade you on something, and part of that is effort of, sort of effort level, and some of that is ability to synthesize and apply concepts that we're hopefully learning in class, or I'm intending people to learn in class.
Okay. All right. We'll give the proposal to be a little bit bigger, grander.
Well, I mean, so
and less, you know, maybe concrete.
I would think a proposal would probably have 2, maybe 3 aims in it, and you know, they don't have to map exactly to specific papers, but you know, you may be thinking about a K. Some of you may think about K awards or F awards, or even something as small as a University Research Foundation grant, which is up to 50K, which is not nothing. You're probably not going to be like, in my grant, I'm just going to download a data set and search around for it aimlessly until I find something I'm interested in studying, which is what you may very well do for the first project. And that would be, if you're going to search around aimlessly, better to do it for the data analysis than for the proposal. The proposal ought to be more conceptually cohesive.
Okay.
Okay. All right. Wow. So back to the grind. Week, I think 4. I can't remember anymore. So first, your weekly Tuesday schedule reminder. Speaking of assignments, the next deliverable is due now in 2 weeks, and that's the data analysis setup, which hopefully none of this is new before. And then just remember a week after that, so in 3 weeks from today, is the second assignment to be due, which is the first dipping of your toes into the research proposal pond or pool or whatever it is. All right, so today, kind of a slightly bifurcated class, but they actually have a fair amount to do with each other. First, I want to finish up I want to cover material that I didn't get to from last week on how to model binary dependent variables. And that's going to be more kind of pragmatic. And then we'll go back to this topic of controlling for covariance to talk about some conceptually how regression works, how it relates to matching, and then introduce the propensity score as a potential alternative or complement to regression analysis. It's a technique that's taken off in the last decade, and a lot of people use it, and it sounds cool because it's different from regression, but it turns out they're intimately related, and it doesn't get around a lot of the same problems that regression has also show up, or a lot of the problems that regression has also shows up when using a propensity score. So I think it's important to know, A, how to do it, and B, sort of what its limitations are as well. As usual, feel free to ask questions at any time. So first off, binary dependent variables. So the most, I think a normal place to start with binary dependent variables is to say, well, let's run ordinary least squares regression or linear regression, same thing, on a binary dependent variable. So just, I'll show you this example in a second, just regress some dependent variable on a bunch of covariates. What are the potential problems? This is sort of the common approach is, why is this not a good idea? Well, one possibility is that the predicted probabilities that you get from this model could be outside the 0-1 range. So if you're trying to do a risk model, and the model tells you someone has 110% risk of getting, dying within 30 days, or negative 5% probability of getting, the disease, that doesn't make any sense. So it's incoherent. And as I'll show you, that's certainly a potential problem with ordinary least squares, but it's not always a problem. And then there's another problem which is built into using linear regression with binary dependent variables, and that is innate heteroscedasticity. So I told you a little bit about heteroscedasticity last week. Its partner, homoscedasticity, so they're sort of equal variance or variable variance for the hetero part, is a problem. It threatens the standard errors. So what happens if we have heteroscedasticity? We get inefficient estimates of covariance. We also get biased standard errors, so our inference may not be exactly right. There are some techniques to improve it, generalized least squares, which I'm not going to really talk about. But there's a very easy way to make standard errors robust to heteroscedasticity in Stata, and it's called the robust option. I'll even show you how easy it is to do that. This isn't to say that if you use the robust option, you get around this heteroscedasticity in general, but that you could address it. This isn't automatically a problem, and there's a key advantage to using linear probability models over alternatives, which I'll show you coming up, like logistic regression, which is that the coefficients are immediately interpretable. And so when you see an ordinary least squares coefficient, you know exactly what it means. There's nothing, you don't have to do anything to it. It has a standard sort of intuitive interpretation. And that's going to be particularly useful when it comes time to talking about how to interpret interaction terms, coefficients on interaction terms, which we'll get to starting Thursday, I think, when we're talking about difference and differences. So these are sort of the pluses and minuses, at least seen from someone who you'll see has a particular perspective on this, but it's not really shared by everybody. So if we want, here's an example of a linear regression on a binary dependent variable. The command is up top in the blue box. Simply type regress. The dependent variable is DES. This is from the DES data set. Did you get a drug-eluting stent as a function of a bunch of covariates? Payer type, a race type, a diagnosis category, and a continuous measure of comorbidity count. I subset the sample to just the most recent year of data we have in the panel, which is 2011. So just if year equals 2011, comma robust. Comma robust says, dear Stata, please give me the heteroscedasticity robust standard errors. They're not perfect, but they go towards addressing this heteroscedasticity issue that's built into linear probability models. And so anytime you run an LPM, linear probability model, you should ask for the robust standard errors. It's a piece of cake. So this is standard regression output. So Stata doesn't care, or doesn't even know, or doesn't care that you're running linear regression on a binary dependent variable. The output's going to be the same. Tells you the number of observations, tells you what the model is statistically significant as a whole. So we see that the F statistic is 0.0000, which is very small. So what that means is that these variables together jointly explain a significant portion of the variation in whether or not an individual level patient gets drug-eluting stent. And then we have an R-squared, although I caution you not to use the R-squared, not to interpret the R-squared literally, because it doesn't mean the same thing you think it means when you have a binary dependent variable. It's still useful as a measure of thumb, but it's it's not literally the proportional variation explained by these variables, but it still gives you the calculation. Now, how do we interpret these coefficients? We've got a set of coefficients, so let's focus on payer category. It's a categorical variable. It takes 5 values. The omitted referent is commercial insurance, so patients who were, had HMOs or PPOs, probably through employer-sponsored health, but not necessarily employer-sponsored health insurance coverage, but not necessarily. 2 is Medicare. There's no way you would know this except for the fact that I'm telling you. 2 is Medicare, 3 is Medicaid, 4 is uninsured, 5 is other. So the coefficient on 2, which is Medicare, is negative 0.085. In English, my best effort in English anyway, patients with Medicare insurance have an 8.5 percentage point lower likelihood of getting a drug-eluting stent, on average, controlling for the other covariates in the model. Is it significant? T-statistics 24, p-value is 0.000, highly significant. In other words, if you have Medicare, you're less likely to get drug-eluting stent during this time period. If you're Medicaid, you're 11 percentage points less likely to get drug-eluting stent relative to the omitted referent, which is commercial. And if you're uninsured, you're almost 30 percentage points less likely. Notice my use of percentage points rather than percent. These are additive units of probability. So these are literally percentage points. We're talking about, just between, say, the probability in the commercially insured category was somewhere around 85%. Medicaid would be 11 percentage points less than that. Is that all right?
Sorry.
No.
So it's the difference rather than the absolute.
It's not a multiple drug. Well, no, it is the absolute probability of getting a drug state, but it's in absolute units of difference. It's in arithmetic absolute units of difference rather than a relative difference. This isn't, when we say 10% higher, you mean 1.1 times higher rather than 10 percentage points, which is 10 percentage points, 10 units of probability lower or higher in an additive or subtractive arithmetic sense. So that's really important because that's what we have as a linear model. We're assuming the effects are additive to each other. So
should those all add up to 100?
Do these all add up to 100?
All the coefficients?
No, there's no reason they should either. Because we're just saying, are they conditional on having Medicaid? What's your use of drug-eluting stent? It's 8.5 percentage points lower than if you were to have commercial insurance.
So if the coefficient's like 85%, can you say that Medicaid, it's whatever 85 minus 8 is, it's...
Yeah, 70,
okay.
Yeah, that one.
Okay.
77. So we know, right, so what do we know from a linear model? We know that somebody who was omitted referent for race, which is white, omitted referent for commercial, which is, for insurance, which is commercial, omitted referent for diagnosis category, which I think is MI, and then had 0 comorbidities, has on average, or has, the rate of use of drug-eluting stents in that group is simply the intercept, the underscore constant term in our regression. So it's 80%, right? So that's what I probably should have said. So relative to that, holding these other factors constant, the difference is 8, 11, 30, whatever, 29, 30, whatever. Any questions about that? Because this is fundamental to understanding just how to interpret. You see a regression, how do you interpret it? You interpret it the same way whether the dependent variable is continuous or binary. You just need to know what units they're in so you can make sure you're talking about percentage points or days of length of stay or whatever it is that you're talking about.
Can you just explain one more time the difference between robust standard error and standard error and when we should use the robust?
I didn't actually tell you that much about. So the robust estimator is an empirical add-on to basically address the heteroscedasticity issue. So in normal linear regression, you may or may not have heteroscedasticity. You can diagnose it. There are more efficient ways to address it if you know the form of the specific form of the heteroscedasticity. But in most cases we don't, and it's become kind of prophylactic to say, especially in linear regression in particular, there may be heteroscedasticity, but I'm going to be using robust variance covariance matrix. So my standard errors now say robust on top of them, and so my inference based on those is based on this. The basic idea is it's kind of a, I think of the right analogy, but it's not perfect, but it works most of the time kind of thing.
So we just,
well, I wouldn't say blanket statement, but if you're using linear regression, probably. At least see if it makes a big difference and understand why. Like, it's something to think about. If you're using a linear probability model, definitely put on the robust standard errors. It's a piece of cake, though, to rerun this model and remove the comma robust, and you'll get the standard analytic standard errors, and you can see how different they are. By and large, I'd say it's not trivial, but it's a second order concern, especially in this class, relative to making sure, or to trying to make sure that your coefficients are as close to causality as we can get them to be, given our conceptual framework. So inference is important. People spend a lot of time working on it. On the other hand, there's reasons why people spend a lot of time working on inference, making sure the standard errors are right, because there are things that we can do about that. And robust standard errors is just one of a variety of potential corrections and manipulations and things that I don't have time to go into and really aren't on the path for understanding causality, right? Because the accuracy of the coefficient is an issue of bias. These coefficients do not change with or without the robust adjustment. The only thing that changes is a standard error, which means then that the p-value, the t-statistics and the p-values change, but they don't affect whether or not these coefficients are estimated accurately. And notice that there is no, Stata doesn't tell you these coefficients are or are not biased. That's not something Stata can tell you. That's a conceptual issue that says, what's the concept? What is our model? And we'll get into that some more going forward.
And those coefficients, each one is holding all the other variables constant.
Yes, and they're average estimates. So what that means is for Medicaid patients on average, not necessarily for any particular Medicaid patients, but for Medicaid patients on average, that's their difference in the use, holding constant race, diagnosis category, and comorbidity count.
Is there a way so obviously within pair category you can see the different amounts, the different pair categories, but is there a way from this to say like how influential pair category is as a group on drug-eluting stent placement as opposed to race or diagnosis or something, or you really only look at it broken down into the different types of pair?
How would you do that? I mean, we've talked about this kind of in the context last week a little bit about cross-model. So I think the question you're asking is, does pair category add information to...
I guess you do it without pair category?
And see how much the R-squared changes. And that gives you some sense of... So that's an immediate test of, is pair category adding anything to what we know? Now you can do that. There's a whole procedure about basically kicking out variables and putting them back in and seeing how much R-squared changes. But you have to do it in a reasonable... You just got to make sure you're thinking it through and comparing it to what? Because the R-squared change only tells you kind of with and without pair category relative to whatever else is also in the model, and that's where the rub is. Because if there's something else in the model that's highly collinear with pair category, then it's not going to add much to the model.
This is what you were saying. It needs to be a nested model.
Well, so with it, to do that the F test, which is the look at how much R-squared changes, you need to, kind of a model with and without pair category. Two models with and without pair category are by construction nested, because one has pair category, the other one poses a zero coefficient on all the pair categories. All right, cool. So moving along from linear probability models, then. How many people are familiar, or at least have heard of logistic regression in any context? All right, a little bit. Okay, so Tim's going to, towards the end of the semester, you'll get into the more nitty-gritty of what logistic regression is. For now, I want to stay at a pretty high level of just sort of explaining that there's alternatives out there. Because I need to reference it. It's a commonly used technique in the context of propensity scores. I don't expect you to have an intimate understanding of logistic regression after the next 5 minutes. I'd be surprised. But the general issue is there's a fight out there. There's a war going on between economists and statisticians, between cats and dogs, about whether or not linear probability models are good enough for what you want to do, which is what the economists say, versus the statistician / epidemiology perspective, which is only a real ding-dong, like an economist, would use a linear probability model when you can use something better like logistic regression. And so I'm here to say I don't think ordinary, as a contrary member of the American Economics Association now, there's nothing actually wrong with ordinary least squares regression per se. It does have limitations and you need to know what they are, but it does have some important key strengths as I've already outlined, primarily is the interpretability issue. But at least logistic regression is out there, and I'm going to show you, it addresses exactly the limitation that linear probability models have, which is making sure that your predictions are within the 0-1 range. We'll get to that in a second. But first, let me motivate logistic regression a little bit as a first pass. So linear probability models, we're just modeling the dependent variable 0-1. The coefficients are then interpreted in terms of percentage point differences in the use. It's an arithmetic difference. Logistic regression is going to use odds. So to get the odds, though, we have to start with probabilities. As hopefully you're all aware, when you have a discrete set of mutually exclusive and exhaustive options, like heads or tails from flipping a coin, their probabilities have to sum to 1. So let's say we have a binary outcome, probability of success, probability of failure. Your probability of success is, say, 0.8 or 80%. Easily enough, your probability of failure is 0.2, or 1 minus the probability of success. The odds of success is simply the ratio of the probability of success divided by 1 minus the probability of success, or the probability of failure. So you get this ratio of probability of success divided by the probability of failure equals 4. If you do the odds of failure, you're just taking the reciprocal. The odds of failure then are 1 to 4, or 0.25. And notice that, I already said that these things are reciprocals of each other. Odds, because we're taking the ratio of two numbers that always have to be between 0 and 1, the range then of an odds is between 0 and infinity. That should be, I hope that should be pretty straightforward. And you can go between odds and probabilities. If you know one, then you can reverse engineer the other. So if the odds of an event are A to B, then we can back calculate the probability of that event as being simply A divided by A plus B. So if your odds are 2 to 3, the probability of that event occurring is 0.40. Highly helpful if you're ever thinking about getting into betting, or if for some reason all bookmakers talk about stuff in terms of odds, or at least not everything, but there's no talking in terms of probabilities. Talking about it in terms of odds, especially talking about horse racing. It's a 4 to 1 or a 1 to 4. Like, just tell me the probability that they think they're going to win or not. Much easier, but maybe that's part to cloud the market and take advantage of suckers who don't understand probability. Or maybe not, I don't know. But then, so the next step to go is say, okay, we have the basic concept of an odds. Now let's think about odds ratios, where we have the likelihood of getting, say, an outcome occurring. Let's talk about the likelihood of getting a particular treatment in two different groups, men versus women, for example. It could be any groups, whatever. The odds ratios are going to turn out to be simply the ratio of the odds for men to the odds for women. So, I chose poorly in terms of the actual example here. So we have males. I said, suppose males have a 70% chance of getting the medical procedure, while women have a 30% chance, which was unfortunate. I should have chose something that wasn't the inverse, because the probability that females get the same procedure is also the same as the probability that males don't get the procedure. But regardless, the example works out fine. The probabilities for male are the 70% of getting it, 30% of not getting it. For women, they're reversed. And then so the odds for male of getting the treatment are 0.7 to 0.3. So 0.7 divided by 0.3 equals 2.33. And the odds for female, that's the probability of success, divided by the probability of failure, is simply the reciprocal, 0.43. We can then compute the odds ratio, which is a ratio of odds, which are themselves ratios. So we now have the odds ratio for the likelihood that men are getting the procedure relative to the likelihood that women are getting the procedure, or it's the odds actually, 2.33 divided by 0.43. In other words, the odds that, the odds of a male receiving the procedure are 5.44 times as large as for a female to receive the same procedure. Not on average, and this is not a regression context, but this is what we're going to be getting out of logistic regression. Why is it nice? Well, I mean, it's understandable, although I don't like odds much because I get, especially odds ratios, we start to get confused about what's going on, and they're not probabilities exactly, but but that's what we got out of logistic regression. So let me show you some of this. This is logistic regression in a nutshell. Please ask any questions at any time. I'll try to do my best. You're going to get more of it later on. Logistic regression is a regression technique where the dependent variable is assumed to be binary, 0, 1 outcome. And then instead of modeling the probability directly like we did in the linear probability model, we're going to model what's called the logit function of the probability. So the probability is called P. And the logit function is simply the natural log of P divided by 1 minus P, which is the odds of P. So those are what we call the log odds. And then we're saying that thing is now a function, same kind of regression setup of an intercept and then these products of coefficients and covariates. I don't put an error term in there. It's not conceptual that there isn't one. It's just that we don't need one per se because there's already uncertainty built in by virtue of the fact that we're modeling probabilities instead of actual outcomes. But whatever. So if I just put the probability of P equals 1 right here, that would be a linear probability model. Instead, I'm manipulating this outcome to take the logit of the probability. It's going to have some nice benefits. But notice this becomes what's called a nonlinear model. Because we're doing something, we're transforming the dependent variable. There's going to be a whole set of types of regressions under the rubric of generalized linear models that are themselves nonlinear. They're based on the linear model, which is ordinary least squares regression, but they're going to be this whole modification. I'm telling you they're out there, so you won't be surprised when you hear about them. I'm not going to say too much about them, except that logistic regression is simply an example of one of these. Why are we bothering with log of the odds? Well, so it has some nice mathematical procedure. Simply, if the odds range from 0 to infinity, taking the log makes sure that then the log odds ranges from negative infinity to positive infinity, and is symmetric, which is convenient computationally. And it also has some benefits mathematically, which we'll see in a second. What is the logit transformation? So if we start with this idea, I'm just calling xb equal this linear predictor set, right? This is just simply meaning the product of each coefficient and its covariate plus the intercept, call it xb. Okay, if we then, if we say the logit of p equals xb, or so the log of the odds of p equals xb, we can solve for p in terms of xb, and we get the probability of the event is now e to the xb divided by 1 plus e to the xb. So this is basically a mapping from negative infinity to positive infinity of the log odds to a probability space. This mechanism right here guarantees, let's pick specifically, to guarantee that any time we have wherever we are in the log odds space, we force back now the probability to be between 0 and 1. When xb is negative infinity, the probability is 0, or asymptotically approaching 0 because it eventually gets to negative infinity. Same thing on the positive side of the 1. And when the xb equals 0, it's the same thing as saying the probability equals half. Stone silence. How does this look when you line up the linear probability model and the logit function? This is what I was talking about before. This is our old linear probability model. There's a straight line right between here. What's the problem? Well, one of the problems besides heteroscedasticity is that if we extend this line any further, we're going to be breaking the 0-1 boundary. For x equals 40, we're going to have a predicted probability of being somewhere above 1.5, right? Does that make any sense? No, it doesn't make any sense because probabilities are defined to be between 0 and 1. Same thing if we went down to x equals 20, we're going to be somewhere down in the negative range. Does that make any sense? Of course not. Same thing. Has to be between 0 and 1. The nice feature about the logit is that the bumpers are put on for you. That was a whole logit transformation. It's now, even though it looks like this slope is kind of similar right here, more or less, however far out you go on x, you're guaranteed to stay in the 0-1 range. What's the implication of this? If you're coming up with a risk model or needing to do anything involving prediction, the linear probability is probably not going to be as useful as logit because of this possibility that you're predicting outside the 0-1 boundary in a risk model or something, right? Okay, so I'm perfectly fine conceding that. I would definitely use logistic for the same thing as anybody else. And I don't think anyone is saying linear probability models make sense for prediction in that setting, because why would you do that? You can use logit, or there are other things like probit or log that have the similar kind of bumper set. And then the issue is, what does this function look like? In particular, how fat are the tails in terms of whether you want to use probit or logit. But by and large, those are all pretty similar. So back to the OLS versus logistic regression comparison. For OLS, we usually have a continuous variable. We can use binary variables here, or any kind of variables. Again, just to summarize, the coefficient interpretation is a beta unit change or difference in the outcome y for a 1 unit difference in x, holding everything else constant on average. Logistic, we're constrained to only modeling binary dependent variables, and the coefficient interpretation is a beta unit average difference in the log odds for a 1 unit difference in x, holding all else constant. If you ever see someone write ceteris paribus, it's Latin for holding all else constant. It's kind of what snotty economists do sometimes, because they can't be bothered to write holding all else constant. They just write ceteris paribus because it sounds cooler because it's in Latin. I do it, and yet I feel embarrassed about it. Part of that, I think, is a signaling thing, though. When you're talking, like, if you want to be part of the crowd, you're like, oh yeah, ceteris paribus. But it's not language I would use around the house. So let me show you the same model as the linear probability model that we already estimated, but now in small type with the top box is a logit model. The stated command is logit, dependent variables DES, same set of covariates, race category, pay, diagnosis category, comorbidity count, if year equals 2011. I don't need the robust standard errors. It's not an issue here. There's some advice about whether you should use them or not. I don't have strong opinions about it. Note that we get this iteration information, logit, logistic regression, most of these are called maximum likelihood models, so they're not necessarily guaranteed to converge. Whereas ordinary least squares has a single unique solution in terms of coefficients for a given data set and a given model, maximum likelihood models are not guaranteed to converge. They almost always do, but what they're doing basically is searching for the optimum. It's not it's not an analytic solution where I was able to take the derivative and show you there's a single unique solution. And so that's one difference, but that's a mechanical difference or a, under the hood kind of difference. Number of observations is the same. Pseudo R squared. It's not an R squared anymore. It's a pseudo R squared. Again, it's not exactly the proportionate variation explained by the models, but it's something similar to that. So loosely, but not literally. And now what do we get for the coefficients? Let's focus on payer pen again. We've got, so if you're Medicare, you're about there's 6 log odds units less likely to get drug-eluting stent than somebody who has commercial insurance. If you're Medicaid, you're 0.778, almost 8 log odds units, and if you're uninsured, it's 1.5 log odds units lower likelihood of getting drug-eluting stent than somebody who had Medicare insurance. What does that mean? I have no idea. I can tell you that the cardinality of these coefficients is meaningful. The more negative, the less maps directly to a lower likelihood. But I can't tell you what the hell a log odds is. And I challenge anyone who claims that they can is, indistinguishably either really smart or full of crap, right? And I can't tell the difference. So, that's not that useful.
What information does that give you that the other model didn't? What does this give you that's different?
So it gives me a set of estimates as to the likelihood of, the relative likelihood of somebody with Medicare versus Medicaid or commercial Medicare, Medicaid getting drug-eluting stents after imposing this extra structure on the model that the probability that we're not modeling probability directly anymore, but we're modeling the logit of the probability. So it should be giving me something similar, but how we're going to interpret it is going to vary because we have this transformation of the dependent variable. So what this tells me, just like the linear probability model did, is that sort of in descending order of likelihood of getting drug-eluting stents, I'd say commercial has the highest probability, Medicare second highest, Medicaid third highest, we're not forgetting the other group for a second because they're tied for second, and then uninsured, least likely to get drug-eluting stents. Right now, it doesn't tell me anything about what those magnitudes mean, and so we can, in fact, make some more sense out of these. If we exponentiate the coefficients, we then get the odds ratios. So e to that beta, or e to this beta, is an odds ratio, the average difference in the odds for 1 unit difference in x. Note, unlike the linear probability model, which is additive, the odds ratio is multiplicative. So we can then kind of calculate e to the beta minus 1 times 100 to get the average percent difference in odds for 1 unit difference in x. And so we could say, again, our odds ratio is, say, 4.5. We'd say the odds of y are 4.5 times as large for men than they are for women, or for whatever x is when it's 1 than it is when it's 0. And that's the same thing as saying the percent difference in odds of y is 350% higher for whatever x equals 1 is relative to x equals 0. Again, the baseline, when the coefficient is 0, the odds ratio is 1, the percent change in odds is going to be 0. That maps back to the sense that on this output, right, these are still statistical tests of whether or not this coefficient is equal to 0, which is the same thing as saying whether or not there's information coming from, whether or not Medicare is significantly different from Medicaid. We're measuring it here in the log odd space rather than directly in the probability space, but it's the same test. The machinery working there, you're still getting the same kinds of information from a logistic model that you are from a linear probability model. Okay?
What is the constant on?
The constant is telling me the same thing it is in linear probability land, except that the average sort of holding at where everything else is 0, the average value of the log odds of getting drug-eluting stents is 1.5, which is, somewhere north of, so if 0 is 50%, it's going to be north of 50%. I guess I can exponentiate that and tell you what the baseline odds are.
So you do the same thing.
I guess. I don't actually know. I wouldn't normally interpret, I don't know what I would do with interpreting that, because I'll show you a different, well, let me show you first, that's logit, right? If we ask for stata to give us logistic, which is the same damn thing, except now that we get a set of coefficients in log odd space, it's giving us the odds ratios directly, saving us the hassle of having to exponentiate ourselves. So same exact bunch of stuff. I took out the log likelihood crap, same exact pseudo R-squared, same z statistics and same p-values, but now everything is the odds. So this is relative to to commercial patients. The odds of getting drug-eluting stent when you're Medicare are 45% lower. If you're Medicaid, it's 55, 53, and 79-ish% lower odds. What does that mean in English? I don't actually know that well either. I can tell you that the ordering again makes sense, and that the order makes sense, and that the unit difference kind of is meaningful. You can do statistical tests to say whether or not the odds ratios are the same. But I personally don't have a super great grasp of being able to interpret odds ratios, which is where, maybe that's why statisticians and epidemiologists are like, because economists are stupid, and they just can't get it. But because I can't get it, I have a hard time explaining to you something that I understand the words that I'm saying one by one, but when you put it all together and say, this is an odds ratio, like, okay, I understand that this is telling me that if you're Medicaid, you're likely, you're less likely to get Medicaid, less likely to get drug-eluting stents, Medicaid, relative to commercial. I understand all that, but I still don't understand, but the odds are 72% different. Like, I don't have anything to anchor that to. And so, I personally not that I don't advocate using logistic regression, and I think a lot of papers, especially in medical journals, just report odds ratios, which it's not wrong to report odds ratios. You understand that, wow, the conclusion here is that if you're anything but relative to commercial, you're really getting hosed, and if you're uninsured, you're really, really getting hosed, at least in terms of getting a drug-eluting stent is a good thing, which the model can't tell us. But the units they don't come naturally to me, and I'd argue they don't come naturally to most people. So there is this kind of a philosophical question about what's the right measure of association between a covariate and a dependent variable when the dependent variable is binary. In other words, what does the coefficient represent? And so there's three main choices on the menu that you have to choose from. One is odds ratio, which is the probability of the event occurring when sex is male versus the probability of the event not occurring when sex is male divided by the probability of the event occurring for females divided by the probability of the event not occurring for females. That's the one I think is arguably least obvious to, least easy to grasp. A more common and immediately more understandable metric is the risk ratio. Simply, the probability that the event occurs for men divided by the probability the event occurs for women. That's all great. And then the third one is the risk difference, which is what you get out of a linear probability model, which is the arithmetic difference, right? So this is a probability of getting DES when you have Medicare versus commercial insurance is 10 percentage points or something, right? So that's on that scale. You get this immediately out of logistic regression. You get this immediately out of linear probability models. You don't get this. There's a couple models that actually will pop this out. I think you can get out of a Poisson. There's some particular models. The catch here is that the risk ratio is, for these models that estimate it naively, these models don't converge very well. So they're not super attractive in that regard. You can tinker with the odds ratio under certain criteria and kind of say, well, we don't, we get this out of logistic regression, and there's like formulas that people have developed to say, okay, so we just apply this correction, and now it's like an estimated risk ratio based on our odds ratio. It's not particularly satisfying, whereas again, in linear probability model land, pops out something that even simpletons like me can wrap their heads around. Not that any one is better than the other, although I think the odds ratio is least attractive. But so, what you want to do when you're thinking about presenting stuff like this is to be able to say, not only show your readers what the ratios are or the differences are, but also show them what the baselines are. Because if you know the baseline, you know the ratio, you know the baseline, you know the risk difference, then you can compute the other one that you want in a reasonable way to say, well, it's 10 percentage point difference, but that's only a 2% increase in actual risk or whatever. So, I think these are better. Whichever one you choose, try to make sure that you have enough information for the interested readers to get the other one that they want. So let me introduce this concept of marginal effects, which is basically how can we get something like the risk difference out of a logistic regression. So here's a technique which I'll describe to you, or at least you can read about in painful detail. It's an approximation. Let's focus on the bottom half of the category. So let's say you have a variable that's simply like the effect of patient sex on getting drug-eluting stents. So it's either male or female, 1 or 0. We want to know what the impact is in probability space. How do we do that? We can go through this process of basically saying, let's compute the predicted probability for each observation as though coding the person as female, and then compute the same predicted probability coding that person as though they were male. So for each individual, we then have this difference. We have a predicted probability of 45% versus a predicted probability of 72%. Or should I say 75% because that's easier to divide. So it's a 30 percentage point difference for that one observation. For each observation, we have some similar value. 2 predicted probabilities, the differences between them. Simply average that across our set, and we now have an average marginal effect. That is, the marginal effect, the change in the probability, averaged over every observation in the data set. Hopefully that has some, okay, I could write it out for you if it was more useful, but if you actually want to do it, instead it turns out it's actually pretty easy for most situations, especially for non-interaction variables. Margins, comma, dy dx, and then in parentheses, the variable that we want to take the average marginal effect, so that this is the case it's the derivative, it's the same idea, that we're taking the derivative over. So it tells us we have 63,801 observation, comes right after the logistic regression that we just ran, and it gives us a set of coefficients and our effect estimates and standard errors and their confidence intervals. So I did it here for payer category again. You know, Medicare is 8.5 percentage points less likely to get drug-related extent. Right below it, a linear probability model with estimates. And damn if they're not almost, but not quite, identical. Doesn't mean that they're always going to be that way, but you can do a lot. One version of the story is you can do a lot of work with logistic regression to get right back to where you would have gotten with maybe some sort of more careful stuff to get almost the same results you would have gotten from a linear probability model to begin with. Really good question.
So you have to run this after you run the logistics.
Yeah, it takes logistic, it takes whatever model, it's model specific. So it's going to take the results of logistic regression that we just ran and then churn them through. And this calculation can take a while if you have a slow computer or a big data set or lots of different. I'm only computing the differential, the marginal effects for a single variable. So it only has to go through and say for each observation, let me compute 5 predicted probabilities, and then start taking differences between them and then averaging them across observations, and then also coming up with a standard error using the delta method, which I'm not going to say anything at all about. It's some magic, some econometric magic to get a standard error. Are they the same? No. But in this particular example, they vary like starting at the 4th decimal place, which it's not nothing, but qualitatively our results are going to be, again, you're hosed. You know, if you're uninsured, you're at 30%, almost 30% chance lower likelihood of getting 3 percentage point lower likelihood of getting drug-related extent. Now, if you walk into a medical journal with a linear probability model, you got to bring your A game, because even though you wanted the same thing, the standard for a knee-jerk reaction is you're going to get a statistician involved and say, "What? Nobody uses. You don't use linear probability model. You don't use regression on a binary. You use logistic regression." So that, like, you may wind up doing all this work because that's what they expect you to say in the results section. Your method section is now an extra paragraph because we did this and we did that. Even if you're going to wind up eventually coming up with results that are almost identical to, or very nearly similar to what you would have gotten from a good old-fashioned linear probability model. So maybe the answer is, while you're screwing around trying to figure out your data, linear probability models are fine for estimation, but when it comes time for the big game, you want to get, you know, I can point you to examples of when linear probability models have gotten into medical journals. They do happen, but you need to have a lot of citation. You need to say basically why you're doing it, like why are you deviating from conventional wisdom of logistic is the best. And you know, we'd rather you present, for an interaction term, a ratio of ratios, even though we don't really understand it, but then something that we could understand more easily, because this has been, designated to be a bad idea. And so at least you know what the score is, and you can make decisions for yourself. Any questions on linear probability models before we change topics rapidly?
So the way that you would explain this, like in a manuscript, is to say, like in your logistic regression model, like taking the example of Medicare, which is 2, you know, there was I think the odds ratio was 0.55. So you would say like, whatever, they're 0.55.
The odds ratio is 45%.
Okay, yeah.
Percent lower than.
And then how would you explain this? That
So I would
the
say
absolute difference is 8.5%?
Percentage points. So,
Okay.
yeah. Correct. Ooh.
But it's the absolute difference is 8.5 percentage points, assuming that all the other variables are
Oh, constant.
right.
Yeah, but that's true in both models.
Yeah.
What you're not seeing here is that the margins command is coming after the logistic command, and these are all holding. It's the same model. It's just one's estimated to be a logit, one's estimated to be a linear probability model, and then margins
So
does this.
I guess what I'm trying to understand is this is different than like your table 1 where you have like the number of people with Medicare who got a drug-eluting stent. Because in that situation, you're not holding constant all the other things.
Yeah, and then there's this other issue about how much results you actually put in table 1 versus just X variables. I mean, this is, you know, like style and stuff. Some people actually put dependent variable stuff in table 1. Some people just put, let me describe the sample by, stratified by payer type, and see like what the balance is like across payer type, and then table 2 might be unadjusted results, mean, you know, rates of use by category, without any adjustment for other factors. And you could get that with chi-square test, you could get that with logistic regression, you could do the same thing with a linear probability model and not tell anybody, because they would question why you do that. But you can do all those things. Yeah, Tori.
Could you go back to when you had the linear probability model? How do you get the reference probability of the event? So like the probability that someone with commercial insurance will get a drug-eluting stent.
So the expected probability in this case is going to be, so you can actually use margins to do that. I can show you next time how to get so these are differences, right? You can actually get as margins, it's much easier for margins to kick out, regardless of the model, what the distributions are across, so like 80%, 72%, and mechanically, and that's going to be a lot easier than trying to assemble it from the rest of the regression output, because you can only tell like this constant's only with respect to somebody who's got zeros everywhere else. But what you want is kind of like the average group, the average difference, and this is just the average level. This is showing you the difference. If I went back after LPM or after logistic regression and just typed, well, I don't know, they just showed. So margins, but instead of comma, dy, dx, all this stuff, if I just said margins, paycat, space paycat, it will give me that exact thing that you're talking about with confidence intervals around them as well. Then you can actually do cool stuff like kick those into a graph and start plotting them. And you can do some nice stuff like if you want adjusted trends, you can model everything, put year dummy variables in your model or something, and then say, okay, let me then calculate the mean rates and the confidence intervals around them and pump them right out to a nifty little chart. This is all in state I'm talking about, obviously. Okay, so I want to leave behind, in a manner of speaking, the linear probability model per se, and go back to our old friend controlling for covariates. That's all we get on this. So this slide might look familiar. It'll give a number of you, I think, some amount of headache. This is our story about potential outcomes. The same slide I showed you a week ago. No, what day were we? A week ago Tuesday, I guess. The basic idea here, again, just to review, is that our expectation of the outcome, conditional on whether or not you got the treatment versus not getting the treatment. So this is the unadjusted version, or the observable, not controlling for any covariates. This difference can be decomposed into two parts. The observed outcome conditional on getting the treatment for those who got it, and their own counterfactual, which is for those who got it, what their baseline outcome would have been, or what their counterfactual would have been, and the selection bias, which is just the difference in baseline values between baseline outcomes between those who got the treatment and those who actually didn't get the treatment. Okay, so that's same as before. I want to say some more about this and how regression fits in. So I want to understand the conditional independence assumption. I showed you on Tuesday last week that random assignment gets rid of the selection bias problem because it forces treatment status and baseline outcomes to be independent. So that is that there's no difference in your baseline values whether or not you got the treatment versus whether or not you didn't get the treatment. In other words, they're equal to each other. So the causal effect is simply the difference in the observed outcomes. Think about a randomized controlled trial. You randomize patients to get in the treatment or not. You then compare for those who were randomized what their outcomes were to those who weren't randomized. To those who did get the treatment by randomization, what their outcomes were. The expectation is simply their The difference in their outcomes is the causal effect of treatment because of randomization. But we're in a class where randomization isn't available to us. But of course, this does illuminate the idea that if you can get randomization, it's great. We've left that behind. The conditional independence assumption is that assumption that we're going to invoke to make regression results causal. So the basic idea here is that now we don't have randomization, so what we need to make regression results causal is this CIA assumption, or CIA, the conditional independence assumption, which says that treatment status and baseline outcomes are independent, in red, conditional on the observed covariance X. So now we've expanded this statement to say the expected outcome conditional on the treatment and whatever we have in the model, the difference between that for those who got the treatment and those who didn't get the treatment, this is observable, is then the measure of the causal effect conditional on the outcomes. This is the same thing as saying, suppose in our regression model, where there actually wasn't randomization, after we control for all the factors in X, treatment status is effectively randomized. So let's say we're doing something like treatment of the effect of a drug-eluting stent versus not on length of stay. If we could put in our X variable every possible factor that was important for determining whether a patient got the drug-eluting stent or not, then whether or not they got the drug-eluting stent would be effectively like randomization. Would be effective, and then in that case we're saying that's independent, so the treatment status and the outcomes are now, baseline outcomes are now independent, and our results are causal. That's what we're saying if we take a simple regression, and we look at it and say we're controlling for all these things, we're asserting, we're conjecturing that there's nothing left over that matters for treatment assignment. So as soon as someone says, you see someone who says, this is my regression analysis, and I am interpreting these results as causal, embedded in there is the conditional independence assumption, which is the flip side of the omitted variables bias problem. It's the same thing as saying, I don't have omitted variables bias, I don't have selection bias problem here, I'm controlling for everything I need to do. If I control for all these things, then everything within each of these possible combinations of cells, treatment is effectively randomized. And there are cases where this can actually happen. They're very few and far between, I think. But you can think about something like Angrist has an example in his book about I think it's a job retraining program. And so it's like there are a bunch of selection criteria, like groups of categories of factors. And then once basically you control for the categories of factors, the various factors that reflect entry criteria into the randomization process, once you control for those, apparently, given the nature of this particular program, in fact, it is like within each of those cells, men between the ages of 45 and 55 who were unemployed for over 5 years, whatever, within those categories, treatment was, in fact, according to institutional detail, randomized within those cells. So by controlling for those factors, then you're saying everything, after controlling for those X's, treatment is effectively randomized. That is an important point, because we're going to, that's the assumption that we're invoking going forward. Oh yes, Dan.
So, just to, so I'm clear here, the conditional independence assumption just assumes that there are no omitted variables, right? So
it doesn't mean that they're not. It's like by assumption, this is a causal estimate.
So any case where you have potential concern about omitted variables, this assumption would be valid.
This is something Stady can't tell you whether or not this assumption is valid. You can assert it as an author. It's your duty then to justify the assumption, but it's not an answerable, by and large, it's not going to be an answerable issue. And by and large, I wouldn't recommend anyone actually standing out there and saying, in a secondary data context, I assert the conditional independence assumption and these results are causal. I'm Andy Epstein and I approve this message. Because it's not a provable fact. It's a conjecture. So treat it as such. And then you say things like, well, if this conjecture holds, then these results are causal and the implications are dire. But of course, in our limitation section, we can't be sure that the CIA holds in these data because there's always a risk of, or these are the areas that we might be concerned about for violation of omitted variables bias. It's not that omitted variables bias is probably always going to be some kind of problem. The question is how much of a problem it's going to be, and that's where the rubber hits the road. And so it's about arguing as best as you can that your approach to answering the question gets to as close as possible, or closer than anyone else has already got to a causal answer, and understanding where your sort of assumptions may be at risk for violating the conditional independence limit. I'm assuming nothing else matters. Well, that may not. All I got to do is to refute that. All I have to do is come up with one thing that might matter, and your CIA goes away, or then you can argue and culture the names, and that happens in the literature too. So let me walk you through an example of kind of building up from here, and then I think at the end of this, try and show you how regression really is a lot like how regression controlling for something really actually works. But let's start with the unadjusted regression, right? So let's just say, what is the causal effect of drug-eluting stents on length of stay? Here we're going to regress, this is theta e's, we're going to regress length of stay on drug-eluting stents. We're not going to control for anything else. This is entirely unadjusted. We're using the full sample of 711,065 patients for hospitalizations in here. I'm only explaining about 1% of the variation. And what we see is that our not causal effect, but our putatively causal effect, if nothing else were, if drug-eluting stents were randomly assigned to patients, would be about 97 hundredths of a day shorter. Your length of stay is about almost 98 hundredths of a day shorter than if you got a bare metal stent. It's highly significant. That's our baseline estimate, right? These aren't, I'm sure they're not causal, right? Because we know things matter, but if we invoke the CIA and called them causal, we'd be saying that nothing else mattered, and that was our causal effect, right? So let's add just a single covariate, not because I think that that's the only covariate that matters, but I want to unpack this example a little bit more. Regress length of stay on two variables now, drug-eluting stent and whether or not the case was involved primary PCI or not. And so our square goes up a little bit, and now we have two coefficients. We have the coefficient on DES, which is a little bit attenuated, suggesting that there's some correlation between primary PCI and drug-eluting stent. And we have a coefficient on primary PCI. So if you needed primary PCI or got primary PCI, you stayed in the hospital about 7/10 of a day longer. But if you got DES, all over, if you got DES, it's down to about 92 hundredths of a day shorter stay. Okay, not that these are just looking causal, but we're trying to control for things now. And this is interpreted controlling for primary PCI status. So let me show you a different way, an alternative way of thinking about this problem via matching. And matching is sometimes, you can do matching without doing regression, but I'll show you on the next slide, I think they're awfully similar to each other. So let's suppose we wanted to figure out sort of what the effect of getting a drug-eluting stent is controlling for primary PCI and not use regression per se. So let me show you what we have here. We've got 2 by 2 basically. We have column here is you did not get drug-eluting stent, you did get drug-eluting stent. Row here is you did not get primary PCI. Row here is you did get primary PCI. In each cell, there's the sample size, the number of patients who met that criteria in that row-cell combination, or row-column combination, and then the average length of stay for those patients in that cell. So how could we do this in a matching context? We could simply say, okay, let's hold primary PCI constant at 0. For all the patients who did not have primary PCI, they either got a drug-eluting stent or they didn't get a drug-eluting stent. Their average length of stay, if they got the drug-eluting stent, was 2.5 days. They didn't get the drug-eluting stent, 3.5 days. The difference between them is almost exactly a whole day shorter if you got drug-eluting stents. So that's that 99.9939 estimate right there. We can do the same thing conditioning now, or holding constant primary PCI equals 1. Compute the difference here and here. This is a weighted average. And so it's 3.8 versus, no, actually it's not weighted average. Sorry, these are not weighted averages because we're going to weight them in a second. The average holding primary PCI to 1 is about half a day shorter, right? So to compute an overall estimate of the effect, we could then simply take a weighted average of the two groups. In this group, 509 plus 119, They constitute roughly 88.5% of the whole sample. They constitute the rest of the sample, 11.5%. If you just multiply these two things together and add them, you get the weighted average of 0.9386. Not the same thing as what we got when we controlled for primary PCI in a regression context. We got 91.8. So similar, but not the same thing. But before I go on and show you how they are actually connected to, does this make sense to everybody? I mean, this is a totally legitimate way to go.
It just seems so much more simpler.
It does, right? But how would you do now if you had lots of different covariates? It doesn't scale very well, right? And especially what if you had a continuous covariate? Do you break it up into buckets? Well, then it's not the same thing anymore, right? And so how do you do this for a continuous covariate? Well, you really can't. So it works real nice as an example in a class to illustrate how you could do it in a simple situation. Once you start adding lots of covariates or switching to continuous covariates, it's not real easy. But conceptually, it makes sense, right? It's kind of what we're talking about. We're talking about controlling for. We're looking at the differences, holding this thing's fixed, looking at the difference when it's equal to 1, and then computing a weighted average of the two. And so it turns out the regression actually is doing the same thing, but it's using different weights. So let me illustrate. Again, the same 2x2 grid, everything to that side is the same. So same number of people, same average length of stay within that group. Okay? And then we're still going to have the same